try it. Yeah.
Okay, we just start like another section from Quantum T. Welcome everyone. And today I was just planning just to talk a little bit about the Stern-Gerlach experiment. And then I try to do these in 15, 20 minutes, and then we open for discussion. Okay. So let me share my screen.
Long story short, she's on the back line. She'll be back. So, yeah, so that might get a part fixed. It's only something.
Okay.
Just a moment, Carlos. I think I can hear echo at the background. So if everyone can mute in, and then you can unmute yourself if you have any questions, please.
Okay. So again, we are here to another section about the quantum T. Like this, just a round table style to discuss some of the topics of quantum mechanics, and sometimes give some different discuss with different interpretations, not only the Copenhagen interpretation, the standard interpretation. So today I was planning like to just talk a little bit about the Stern-Gerlach experiment, just to give some ideas about this very important experiment about quantum mechanics, and discuss a little bit about the I think the fourth postulate of the Copenhagen interpretation. About this experiment, the consequences of using the postulates about related to the Stern-Gerlach experiment. So let's start. So again, I just put here, but we already discussed these things, the postulates of quantum mechanics. So it's the same slides that I used in the last lecture, and as well as in the quantum hardware course. So I'll just give here, because probably it's the only one that we will use. There's the probability of finding one of the eigenvalues for several possible eigenvalues as an associated with the observed quantity is given by an expression like this, where this P here, this is the probability, and the P is just the projector. This P here is the projector over the eigen subspace of the Hilbert space with the eigenvalue an, the n eigenvalues. And the ket U and I is sum of the eigenstates with eigenvalue degeneracy Gn. So this we have the other postulates, but because we already discussed it, I will skip now, and I just put this here in blue because it's the one that we use in the end when we are in the whiteboard. But before, so again, it's just a Schrödinger equation, the postulate about the time evolution related to the Schrödinger equation and the Heisenberg in the Heisenberg description. But we are interested today in this experiment. So I'll just give a brief idea, a summary of the experiment, what is happening, and try to use like the fourth postulate, that one that I put in blue here, in blue color here, and we see the consequences of this postulate. So here is just a schematic picture that I took from this book, Modern Quantum Mechanics, Sakurai Napolitano. And basically we have an oven that sends up beams of atoms that here considers the silver atoms. And here we have like a inhomogeneous magnetic field. And in the end, we have here these atoms comes and we have like a plate that the atoms will be stopped by this plate. Will hit this plate. And this is the classical prediction, is something continuous. And what was observed was this. So let's give this description better. So here it is. In 22, Stern and Gerlach measured the possible values of the magnetic dipole moment for silver atoms by sending a beam of these atoms through a non-uniform magnetic field. That's the describing that picture. So it's just a summary of the experiment. A beam of neutral atoms, silver atoms, is formed by evaporating silver from an oven. And the beam is collimated by a diaphragm and it enters the magnet. So it's basically here. Here's the atoms, you have this diaphragm that he's saying, the beam of atoms is come here and get into the magnet. And the field that increase in intensity here in the z direction is defined, which is also the direction of the magnetic field itself in the region of the beam. So as the atoms are neutral overall, the only net force acting on them is the force given by this expression, where mu here is the magnetic moment and B is the magnetic field, which is proportional. If we consider only in the z direction, where is the magnetic field is applied, so we'll have the force proportional to the component z of this vector. Since the force acting on each atom of the beam is proportional to its value, mu z, each atom is deflected in passing from the magnetic field by an amount proportional to mu z. Thus, the beam is analyzed into components according to the various values of mu z. The deflected atoms strike a metallic plate, upon which they condensate and leave a visible trace. The metallic plate is this. So if the magnetic moment, orbital magnetic moment vector of the atom has a magnitude mu, then in classical physics, the component mu z of this quantity can have any values that is between -2 plus mu. Okay, this is classically. The reason is that classically the atom can have any orientation relative to the z-axis, and so will also be true of its angular momentum and its magnetic dipole moment. Because classically, the atom could have orientation like, let's say, up, or could have down, but could also have orientation in between. So classically, these all these values here, of course, that this orientation would be like proportional to something related with the mu cosine of theta, where theta is the angle of this orientation, and that's why it could be possible like to have values between -2 plus mu. Okay, but that's the prediction. So that's why it would be something continuous, because it depends of the angle of the orientation. It would be something like this. But now in quantum mechanics, when I'll not show the details here because this is something like that all interpretations agrees. This has no problem. And in the end, I will give like a reference that you guys can see with details how to get this result like this. So the prediction of quantum mechanics can be summarized by an expression like this. So the magnetic moment would be proportional to something like this, where here E is just the electron charge, H bar is the Planck constant, M is the mass of the electron. In this value here, ML is the magnetic quantum number that is given by values like this. So L here, I forgot to put, but this L here is just related to the quantum number related to the magnetic, to the angular momentum, sorry, the angular momentum of the atoms, okay? So which is integer value. So because this is integer, so ML will also be integer because it's given by minus L 5 plus 1, 0, L minus 1, and plus L. Okay? So this is integer. Thus, the classical prediction is that the deflected beam would be spread into a continuous band corresponding to a continuous distribution of the values of mu z on one atom to the next. And the quantum mechanical prediction is that the deflected beam would be split into several discrete components. Furthermore, quantum mechanics predicts that this should happen for all orientation of the analyzing magnet. So it doesn't depend of the orientation of the magnet, of course. So basically, this is here what is observed in the quantum mechanical prediction and what is classically predicted. So this figure here is in this book. I took this description here is, and this figure is in this book here. Quantum Physics, Atoms, Molecular Solids, Nuclear, and Particles by Iceberg and Hesden. So if you guys want to see some details, I have a complete determination of this. I didn't put here because we are interested in discuss not the agreement, but the things that different interpretation of quantum mechanics disagree. So this is just to give an idea for the experiment and the classical prediction and quantum prediction. So this is the observed and the quantum prediction. I think I have a question.
Yeah, Carlos. Looking at the picture of the observed, it looks like you've got two values for mu, the upper one and the lower one. But the equation that you showed us on the previous slide indicates that there should be like a lot of values for mu, one corresponding to every mi.
So ML.
Okay, right. So you got ML, and there's a whole bunch of values. I assume there'd be a different value of mu for each ML. So instead of seeing just two values, shouldn't we be seeing a whole spectrum?
Yeah, but because it's something like this. I mean, the values are here. It's not something like this.
Right, but I'm saying is,
so if
I
you
only
like,
see two
you have
values.
one L, like let's say if you have one L, let's say this L.
Right.
If L is 1, so if L is 1, we would have like -1, the possibilities of ML -1, and 0 and +1. Okay.
Right. So you get -1, 0, and +1.
So, so
we
these
see
figures would be no, but the thing that they are here, they are oriented here.
So I see two bands.
Each
Does
dot,
each band correspond to a value of m?
each dot corresponds to one position, but it's not this like this. So it's like say one this electron here could be here or here.
Right. And so my question is, pointing at the, let's say the center on the top, right?
Yes.
Is that the value corresponding to, let's say, m equals +1, ml
Yeah.
equals +1, and the one on the bottom is ml equals -1?
Yeah, because I didn't show here, but the m is related with the odd another like that was necessary, like quantum number that is the related to the spin.
See, because when the two bands, I'm thinking two bands, two values for ml. One for the top band, one for the bottom band.
Okay.
All right. And yet, from looking at that equation, I'd expect to see more than two bands. I would expect to see a band for each value of ML.
So yeah, but these values, because I in fact I didn't show here, because the ML is some sense related with the another quantum number. That's the number of spin that is given by plus or minus h bar over 2. Yes, plus or minus 1 over 2. This is the number related with the spin, the quantum number related with the spin. But here, when you say like each ML here, because here we have different atoms here, what is observed.
Right.
One, it is depends of the orientation of the magnet. So the atoms is oriented here.
All right, so those two bands are not related to the various values of ML. They're related to the orientation of the magnet? There's
No,
two
it's
possible
related.
orientations?
No, it's related with the ML, yes. But I mean,
All right.
what I'm saying, each dot here is one atom.
It's one atom,
Yeah.
okay?
And if you said like several atoms, these would be what is observed. Not,
Right, I see that. What I'm saying is I see that you have two bands, right? But I'm seeing an infinite number of MLs from that equation. So why is there only two bands?
yeah, but I mean, this is ML, okay? This is the quantum number associated with the magnetic moment. But associated spin number, there is another quantum number.
Okay,
It's
so
not,
there's another, so this is not
that
the full
is-
picture, that equation. Gotcha.
yeah, because the other quantum number is the spin number, which is plus minus 1.5 for the electron, for instance.
Okay.
Okay, 1.5 because it's an electron, because it's like a fermi.
So plus a half and minus a half. Okay, gotcha.
Hmm?
And so that's what corresponds, the two bands are corresponding to
Yeah.
the other number. Okay, all right, thank you.
But the thing here is because this now is not continuous. Okay?
Right.
It's not continuous because L is not L. This is very summary. Okay, that's why it's like confused. I should be something like more. But if you see like the details in this book, like you see, L is discrete, so ML is also discrete. Okay.
Okay.
But the two values are related with another quantum number. That's the number associated with this. This is the number associated with the magnetic moment. Okay.
Okay, thank you.
Okay, so this is the thing that we will use now. So because this thing here, like everyone agrees, in terms of the quantum mechanics interpretation. This was just to give like the whole description. I mean, at the summary of the whole description, what is the Stern-Gerlach experiment. So, but now I would like to use the postulate associated with the Copenhagen interpretation. Okay, so Stern-Gerlach experiment. So I will just give here a picture that we just saw. So in the case of Stern-Gerlach, let me here's just a picture So let's say in the first case, we could have the possibility that the beam, the atom goes up or down. Okay. So we could have up or down according to what was observed. So this is the Stern-Gerlach in the z direction, when the magnetic field is in the z direction. So if up, I will call the state z plus. If it's down, I'll call the state z minus. And the operator associated with this, I'll call sz, and apply to z plus. This will give me just something like h bar over 2 z plus. Maybe this could let the things much cleaner, Bob. And if S applied S minus, this will give me like minus h bar. Okay, so if my atom go up, so the state associated I'll call z plus. Okay, z up, z plus. If down, the eigenstate associated is z minus. And this, the operator, spin operator, S, I'll call SZ because the Stern-Gerlach in the magnet in the z direction. When applied to this state, you give me like this eigenvalue. If applied the up state, the eigenvalue is this one. So far, okay, every interpretation agrees as well. So in the B, so I'll call this B and call this A, sorry, and this is the B. So we are like, when discussing, we have like the orientation, the magnet is in the Z orientation. But we also could have, there's nothing special in the Z orientation. We could have the same, like Stern-Gerlach experiment, but in the X, oriented in the X direction. So if so, we would have like, instead up and down, would have the electron going to the right or to the left. If go to the right, I'll call this X plus the eigenstate. If you go to the left, I'll call state. This would give me h bar over 2 x plus, and this would give me minus h bar over 2 x minus. Okay, and of course this is just like a definition. You could change like the signs, but I just define like up as a positive and right as a positive. Okay, but the interesting thing here is if you have like a sequence. So let's consider a sequential Stern-Gerlach experiment. The sequential we will use like this buff. And then we just like we'll see an example, very simple example, using postulate 2 to like evaluate the probability of where have the atom goes like to up or down direction. Or left or right to left is this, would be like the same. So the So the sequence will be something like this. Consider first a Stern gallop in the Z. So we'll have the possibility to go down, to up, sorry, go down. And then I'll put another Stern gallop X. So see if the atom come here, it goes to the second Stern gallop and it can go to right or left. And the same here. I could put another here. Stern gallop. Possibility right or left. Of course, these possibilities are excluded, right? Okay, and I can represent like the electrons or the atoms that goes up in this first. Okay, we start here, and then we have this or this other one. So it goes up from Stern gallop Z. The atoms that go up from Stern gallop Z are characterized by this. So the Z plus something like this. X plus X minus. Okay, because since I have the possibility up, it can go right or left. So I have this possibility. And the electron or the atoms that go down from Stern gallop in the Z direction would be characterized this way. 1 X plus, and here it's just conventional minus. Because remember that this possibilities, all of them, like X, Z plus or Z minus, for one atom, they are excluded, right? So since X plus, Z plus, and X minus, Z minus are, I think, respectively, yeah, since Z X plus and Z minus, right this way. Since X plus and X minus are mutually excluded as well. Z plus and Z minus. So because of this, so x plus, x minus should be the same z plus z minus equal to 0. Okay, and we can check like with this definition. One can check here z plus z minus. If you use this, that's why this need to change the sign. And this will have plus minus plus. And if you develop here, we'll see that using these properties here in the x, and also remember that x plus minus, okay? This is the identity. So this will give me like 0. Okay? Because this, oh, sorry. This is minus this sign. Okay? So they are excluded, of course. So, okay, so let's use like the fourth postulate. So according to the fourth postulate, let's evaluate the probability from up atom in the Stern galaxy go out to the, let's say, right in the Stern galaxy. So we could like choose another option, down and left, and it would be like the same. It's just a simple example just to show the formalism. So according to the fourth postulate, like the probability to go up, that we are represented like for these letters, z plus, and go to the right, x plus, we'll have like z, and the projector in the x, z. And using, because the state here is not degenerate, we have considered only one atom, this would give me like x, z. Okay, this here is the projector, is this p. And the probability z x plus, if you use like the, as we define as z in terms of x, This is the superposition of x plus x minus times this in the projector in the x state, 1/2 x plus x minus. Okay, and if you do that, we'll find that the probability is 50%, right? Which is obvious. This will go up. The electron that go up has probability 50% to go to the right and 50% to go to the left. Okay, because here this is 1, this is 0, and this is 1, this is 0. So this is the view for Copenhagen interpretation. And we could like change, do more complicated things. I mean, put another sequential of Stern-Gerlach and then we'll go making like the calculations, but we just give more complicated thing, but it's the same idea in the end. So, okay, this is what I have to show. So it's open for discussion. So some comments. Extra comments about the Stern-Gerlach experiment. Or I mean, it's open for discussion if you guys want to talk about another thing. No, I'll stop the presentation. I think it would be better. But if you guys want to see something more, I can show again. So, okay, comments?
So, thank you very much for for the derivations. So, yeah, I think the Copenhagen interpretation, the way you presented is basically textbook quantum mechanics, right? I think what I would be more interested in seeing, which I've actually never seen, is how do you use the pilot wave theory to explain the Stern-Gerlach experiment? That I don't know, because pilot wave theory, I've seen it more in terms of using position and momentum, like in the double slit experiment, but I've never seen it being used for spin. So are you familiar with the formalism of how to use pilot wave theory for spin?
No, I'm just the only things related with the pilot wave I saw was also related with the double slit experiment. I never saw if they have like a different interpretation to the spin, because what I know about they have like a imaginary part, right? In this imaginary part, it has consequences, like in the pilot wave interpretation. The wave function has a real and an imaginary part. And this imaginary part, like, would in some sense contribute. Yeah, but I related to the spin, I never saw. But
yeah,
and the interpretation here is like, yeah, go ahead.
No, I was gonna say maybe I should spend some time looking for it, because I know that there's a lot of people that take pilot wave theory very, very seriously. So I am sure that interpretation does accommodate for spin. I've never seen it, how it's treated, and I think it might be interesting.
Yeah, and the things here, what I'm showing is, as you say, is in the textbook, but I still didn't show like the things related with the relativistic effects. So we have like the Schrödinger equation, that's non-relativistic equation, and the spin. I didn't show the details here, but the spin it comes like an extra postulate that you put another term that's proportional. The Hamiltonian, I'll try to remember here, but the Hamiltonian is, let me.
Yeah, that's one thing that I've heard about pilot wave theory, and is that the reason it was originally proposed is to try to get rid of the wave function as a probabilistic mechanism. So it's trying to make the whole theory deterministic, right? So particles exist and they're guided by this other function, right? So the position of the particle is always known. But one criticism I've heard is that once you try to make pilot wave theory relativistic, things kind of fall apart. And you then need to now interpret the theory as probabilistic as well. So the whole point of making it deterministic falls apart. So there are ways around postulating pilot wave theory to match with relativity, but my understanding is that you have to compromise on the deterministic portion of it. But yeah. I wonder if that separate from how spin is treated.
Yeah. About spin, I'm not sure, but I saw something about the relativistic theory from pilot wave interpretation that exactly as you said. Like, I think if you try like to push to the relativistic this interpretation, like deterministic interpretation, you would violate the relativity, right? So you need like to have the probabilistic, otherwise you could like maintain relativity. And another thing is when you try to use like this interpretation from cosmology, the pilot wave interpretation from cosmology, I think the consequence would have something like you would have like now I'm missing the word, but you would have because the in cosmology the idea is that the universe is homogeneous isotropic, so we have no spatial observers. So in the pilot wave interpretation, at least one of them, I don't know if all of them, so in the pilot wave would be like spatial observers if you apply to cosmology. Spatial observers. So this homogeneity in isotropy, that's part of the standard model of cosmology, you would miss. Spatial observers. So I think this is one of the consequences, but I'm not totally sure. It has problems in cosmology. And yeah, but related to the spin, I don't know. And what I was like first when, because returning to Schrödinger equation, like you have the Hamiltonian when you want to put the spin as an extra postulate. So the Hamiltonian would be the usual Hamiltonian plus spin Hamiltonian. So this is like in the non-relativistic quantum mechanics. That's the way you do. Pauli, I think, did this in the early 30s, I think. And this Hamilton is the usual, like p squared 2m plus v. And the spin Hamiltonian will be something, I don't remember exactly, but something proportional to p. And these would be operators now. This is momentum associated with the spin. I don't remember if it's plus or minus. I think it's minus, but I don't remember. I think it's something like this. So this is like an extra postulate. And it appears when we go like to relativistic theory, but this is still Copenhagen interpretation. You have the possibility when you have like the Klein-Gordon equation that instead use because the P here in the Schrödinger in non-relativistic, this is just like the usual momentum, right? And in the relativistic case, you use like the relativistic moment. So P in the Klein-Gordon version P is the relativistic moment. And you get the Klein-Gordon equation. Now we'll have derivative side. And the spin, but this is you would be like, because of that you will have like associate, but you just has the right results when you have like spin integral. It's the case of photons, for instance, or some type of atoms, because depending of the combination of the number of spins of the atoms. No? The electron has spin 1.5. If you have one atom with 2 electrons, for instance, so you have the total spin will be 1.5 plus 1.5, that is integral. So it works only for, as we call, like for bosons, that particles with spin 1. And the other is the Dirac equation. Dirac. But I'm still in the Copenhagen interpretation. This works for spin same interval like this. So this works for electrons. And in the Schrödinger equation, you put like an extra postulate. But you can explain just some cases. It's not always valid. So if you want like the complete treatment, is like the Dirac that is relativistic, and the spin is equal to the spin for electrons or protons, and so on. But yeah, but this is still like the Copenhagen. And in these two cases here, the special relativity is valid. Okay, more questions, comments?
I do have a question. Excuse me. I've been in and out of this meeting. I've been in transit. But I just thought I heard that there are equations that are different between the Copenhagen interpretation and others. Is that true?
I'm not totally sure. Still, so far as I know, it's only the interpretation different. I think in the pilot wave, they have like, they try like to give in the psi, they have like something like an extra term that's proportional. It's called sometimes like hidden variable. and we have this extra term, and this extra term proportion always has some value that's small, like one lambda, that's a constant, and it's very small, but that the experiments cannot see. But I mean, the Schrödinger equation, you use the Schrödinger equation. But I don't know about the consequence in the relativistic cases. I don't know. As Diego said, like it seems in the pilot wave, you have like problems. You can have problems when you try the relativistic cases. Okay,
Yeah,
Diego.
but there are some interpretations where I don't know if you would say the equations are different, but you do need to add extra terms to the equation. So for example, in some of the more modern collapse theories, like gravitational collapse theories, or there's another one, what is it, objective collapse, I think. You need to add some terms that would induce the collapse.
But is in the equation or is in the wave function, or in the psi? The interpretation is different.
It's not in the wave function, right? It's in the. It will be in the Schrödinger, additional to the Schrödinger equation, right?
Yeah, I'm not sure. Not really sure.
Yeah, I'll have to. I'm not super familiar with this, but I've seen on GRW, right? GRW model. It requires an additional term. Yeah. Yeah, if you look at the Wikipedia page for the GRW model, you can see they explain there. I don't know all the details, but when the problem is they're postulating it as in terms of density matrices. So I can see here the conventional equation in terms of density matrix for the commutator, and then it has an additional term to it.
This page?
Yeah, so if you scroll down, yeah, right there, you see the Schrödinger equation there in terms of rho, the density matrix.
Yeah.
So it's, yeah, and then you see that last term. Yeah, so you have to add an additional term, but I don't know how it works. I have no idea. I know it's there, but I think that term is what causes the collapse.
This here, this lambda, right?
Yeah, I don't know all the.
And probably is small or something like this. This is small, and the experiments cannot see yet. Yeah.
Yeah,
Lambda.
I think the concept of GRW is that you have particles randomly collapse. Like you have a particle, let's say, in a coherent superposition, and every single particle collapses, but it takes, I don't know how many, it's like a really, 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 really long time for a particle to randomly collapse. But when you have millions of particles, then the probability of one of them collapsing and causing a chain effect is larger. So I think that's the whole concept behind the theory. But they have the whole theory, it's formulated in a way that is consistent with standard quantum mechanics, but you have to add these terms that cause the collapse.
Okay, but this lambda here probably is something that you could measure, but it's very small, right? It's the time, inverse of time. It has this value.
I'd like to a bit of a comment and stress something that Carlos just briefly mentioned: hidden variables. A lot of times, when you're modeling something mathematically, if you get into a corner where something doesn't work, you just throw another variable at it. And in a lot of ways, when you look at like pilot theory and some of those, it kind of falls in with that, where it is in some ways different because you throw these extra variables, extra terms in there to kind of correct for reality based on your theory, and you're hoping that somewhere you can figure out what those terms are later down the road. I think that's what's going on here. The example you just presented, G or W theory, is, again, you got that extra term, they shove it in and make everything work. And it might be the way to go, and it might not be. Only time can tell. Another comment I wanted to make with pilot wave theory is that I think it adds another animal that we're not used to seeing, called the hidden wave or the empty wave, which has got its own theoretical implications and set of equations that would make things look a little different than, let's say, a quantum or a classical or the Copenhagen interpretation of anything. That's all.
Yeah, I agree. I think with pilot wave theory, you know, the original idea, I think it was very nice. So you have this guiding wave that guides the particles, and then you have the actual particles are always deterministic, right? There's no probability to it. But I think it does add, and again, I'm not an expert, so I'm sure that people have different ways of explaining the issues with it. But my understanding is that, first of all, it is non-local hidden variable theory, which means that if things are really physical and real, you have true non-locality, which violates relativity, right? And that is I think a serious problem. I'm sure that there's some explanations on how to get around it, but that's one issue. Another issue, from my understanding, is that there's this concept of non-contextuality in quantum mechanics, which basically is showing that depending on how you measure things, the order in which you apply certain observables changes the results. And pilot wave theory, my understanding is that it's not consistent with contextuality or non-contextuality. So there's no way to really say that the theory, it's you know, in its standard form, it's consistent. So that's another issue from my understanding. And what I've heard is that for the relativity part of it, then you have to give away determinism, which was the original reason why you would propose this. And yeah, so it has its own set of issues.
Yeah, so far as I know, all different interpretation will always have like some issues. That something that is not, it's not trivial, that you need to accept. So as Copenhagen, like the probabilistic nature of the wave function. Like the Schrödinger equation is deterministic, but the thing is the probability, the psi that you measure, what you see is the probability, is not the psi. And this, I mean, is different from the classical physics, that you have a deterministic and you measure the things like the position of the particle, velocity, and so on. But you always have some issues in a different interpretation. At least, at least the things I read always have some problems, some issues. Yeah.
Yeah, now the thing is that the proponents of each interpretation will always give you an explanation to get out of those issues, right? So,
Yeah.
but the question is, how convincing are they? And I think what really the conversation should be about is, well, what are the ways in which we can test one interpretation versus another, right? And we've talked about this in another meeting, but does one interpretation have more predicting power than others, right? And what type of predictions can you get from one that you can't from the other? I think those are the questions that are of more interest in what people should really focus on. And my understanding is that there are some proposals to test different interpretations, but the technology is not there yet to do it. So, for example, I saw recently this paper from Sean Carroll. He's a famous science communicator and physicist. He actually has a paper proposing how to test, I believe it's many worlds interpretation versus this GRW collapse theory. And the way it's done is by looking at conservation of energy. So apparently in collapse theories, there is some violation in overall conservation of energy, whereas in many worlds, energy is conserved. So he's proposing some experiments that, according to the paper, are within reasonable values to be tested. It's just maybe the technology is not there yet. But potentially you could check for this energy conservation. And then there's also David Deutsch's experiment, which I think it's a little bit more out there, and I really don't know if it really tests for the multiverse theory or not. But yeah, in that one, the idea is that you have like an intelligent AI connected to a quantum computer, and you can run this test where the AI will split into multiple universes while you're running the experiment, and then the universes will merge again coherently, and then you can ask a question that would tell you for sure if there are multiple universes or if the measurement collapsed. So I think that one's interesting, but it also seems, with all the advancements we've been having in terms of quantum computing, I think that that idea is becoming more and more likely to be implemented at some point.
Yeah. Yeah, I think if we have like a quantum computer, this would be more possible.
Yeah.
Because we have like a big laboratory now to see different things. Yeah, but I'm planning to the future. I mean, maybe we should, like, the next time talk a little bit about because I think it is important about the Einstein-Podolsky-Rosen paradox.
Yeah.
And the inequalities, the next two, two different, because one will not be enough at time. But I think this would be one section for EPR paradox and the other for Bell. And then we go to I tried to see other, like the Bohm theory, like and the GRW and so on, because I think I think really starts with the EPR, right? Einstein was had problems with the interpretation in others, but the EPR I think was like special.
Is it me or Carlos is away?
He froze. I thought the problem was on my side, so I was trying to change my internet connection here.
I see Zulip, because last time also it happened. I think he just disappeared. He wasn't aware. He thought he was on. Let's see. I'll ping him on Zulik. Yeah, so I sent him, I pinged him. Okay. Maybe he will join again.
You're muted, Carlos.
Yeah, my internet collapsed.
Okay.
I'm back, but I think we lose the. Oh no, we're recording. Okay, so it's good. So I'm back. So that's the thing. I was thinking the next section discuss about EPR paradox, because I mean it's important and historically important, and I think when it starts like because the Bohm, the Broglie theory is from the 50s, so the EPR is in the 30s. So I'm trying like to first was the double slit, Stan Gallop, EPR, and discuss about the Bell. And or maybe before Bell we could like follow the history and go to the Broglie, Bohm, the Broglie theory after EPR. It could be good.
I was going to say that I've heard of EPR for many, many, many years. You know, it's a very common thing to talk about when you talk about quantum mechanics. But I had never read the paper, and I read it a few months ago, and it's surprisingly easy to read if you know a little bit of quantum mechanics. And it's very short. It's only like 2-3 pages long. So I think my suggestion for everyone I meet now is you should always read the paper. It's you know, very simple, very easy to follow, and very to the point.
Yeah, Bob's agree. Yeah, this paper in the Bell, the two Bell papers also well written about the experiment, the theorem, Bell theorem. Both papers are very good too. So yeah, so maybe this could be like a homework. Read the EPR, I think Podolsky and Rosen paper, and maybe in 15 days, something like this, we are back and to discuss. And I show something in the because we are still like looking for the best for the form to present here. So I tried like the first two very important experiments, double slit and the Stan Gallop today. And now let's go to things more I don't know, interesting, but I mean it's both interesting too, but more polemic, like EPR paradox and so the things. So we could like follow the history of EPR and see the theory from the Bohm de Broglie, and just after, because the Bell papers are from the 60s, so you could see like in the EPR in the 30s, a Bohm theory is from the 50s, and Bell in the 60s. It could follow this.
And I think it's good that way, because there's not only, you know, the years to follow, but each of them was inspired by the previous one.
Yeah.
So the reason Bohm came up with his theory was trying to solve EPR. And the reason Bell came up with his inequalities was because he was actually obsessed with this fact that Bohm had created this theory that apparently in a book by von Neumann, it had been written that it has been proven that there's no way to have there's no way to have this hidden variables, and Bell was seeing Bohm's theory that had hidden variables, and there was a conflict, and that's what inspired him to look into the theorem.
Yeah, and Bell makes some criticism about the von Neumann proof as well.
Yes, yeah.
So, about link for a paper.
That's a EPR.
EPR, it's still open here. Okay. Yeah, so this could read 4 pages only, and the paper is here now, Bob.
That's very nice. It's only like 3.5 pages, right? It's really short.
And if you guys see in some books, it also has like the EPR. I think is the, I don't know if it's here. Yeah, in the Grifts. In the Grifts, they discuss the EPR as well. Is this book? Unfortunately, I have only in Portuguese, but it's in English originally. This book. It discuss the EPR. The author is David Griffiths. You guys can, because to me, when you have the books in Portuguese, is cheaper. So I buy in book. Only few in Portuguese. So this is the author, David Griffiths, quantum mechanics. It discuss. In the end, it discuss a little bit. But this type of discussion is not common in the textbooks of quantum mechanics. Like most of the textbooks are the famous like shut up and calculate. Not have these discussions. But this one has. So okay. So we could like stop here, or you guys want to just have more comments? No, I don't know if Bumble is here. Want to give some add?
Yeah, I had some announcement stuff, but I think it's better to do that in the quantum hardware course thing. Yeah.
Okay. On Friday next Friday. Yeah, because say here that my connection is bad. So if I collapse again, so.
Well, maybe we can end it here if nobody has anything else to comment. Thank you again. Amazing session. I couldn't join really because I was in a conversation with my colleague about something else, but I was listening. Yeah, so it's great to see the engagement. Yeah, and to everyone, we will follow up with you about when the next session is. Yeah, and I might actually invite someone to give a talk about something else, but I will talk to Carlos first. So we put it under maybe when we have a break from quantum T, one of the weeks when we are not having this roundtable, maybe someone, because I think quantum T, this open debate format could be something, a good platform for that. Yeah, it's to do with someone who wrote a very critical paper, a constructive criticism, in my view, about the state of quantum computing. So yeah, the paper has received a lot of praise and criticism as well for those who are a little bit more optimistic about the quantum computing, but it does make a very good arguments about the other side as well. So yeah, I'm looking to kind of close a date with him, so we can announce this. Yeah, so I think quantum T could be a good forum for us to have such a. He will talk about the paper he published, his critique, and then we'll have like a roundtable discussion about. People can share their opinions and so on. Yeah.
Okay, good.
We'll try to do it in one of the weeks where we have a break from the actual quantum T core coverage to do with the interpretation of quantum mechanics. But I feel that quantum T is actually a good forum for this. So we're actually incorporating also debate about quantum information science. Yeah. Okay, so that's all I wanted to share. Maybe we can stop sharing. And if anybody wants to say anything. I don't know, Carlos, you want me to stop recording or you?
Yeah, I will stop now.
Yeah.
Okay, so thanks everyone.
Yeah.
So see you guys in the next section.
Yeah. See you all. We look forward to seeing you again in Quantum T in the next session.